I'm Navneet Sharma, and today we would be discussing a topic called error detecting codes. Whenever we need to communicate in binary or in digital communication, what we do is we transmit a given signal, a digital signal from point A to point B, where point A is our transmitter, point B is our receiver. So what we expect at point B is that whatever we had transmitted from point A is received at point B without any error. For example, if we are transmitting a 4-bit binary code, say 1101 from A, we expect that it should be received as 110 and 1 at B. In case if there is some error which is involved, we are transmitting say 1101 and we received 1001. We can see that the second bit is in error. Unless some checks and measures are not taken, the receiver would not be able to know that some error message has been received, and it would continue processing the wrong signal or the wrong message. So this is what we are going to discuss today, that how we are going to transmit a particular signal along with an information that there is some error in our message. For that purpose, we would be using parity encoding, Parity encoding is of two types. First, even parity. Second, odd parity. What we do actually is we take on this message signal. Say this is 1101. Now we are discussing about even parity actually. What we do is we add one extra bit to it, which is known as parity bit. Along with this message bit. And now, despite transmitting 4-bit, which was actually our message, we would be now transmitting total 5 bits along with the parity bit, and the receiver would also get the 5 bits. Now, in this case, if we are encoding this in even parity, what we would be adding here would be a digital value 1. What we check is the total number of 1 in our message bits. Here the total number of 1 is actually odd. So what we do is we add one extra parity bit to make it even, and our final message would be 1101 and 1, which is containing an even number of ones. Let us now take on another example. Here, if we are encoding in even parity, what we are adding is a digital value 0, so that the message bit, which was already having even number of ones, contains even number of ones even after encoding, and this is the final signal which we would be transmitting. So if we take on any message values, any message if it is encoded, so whatever message we are taking, we are adding one extra bit to make it even. So the even message is being transmitted all the times. If it is not even, as in this case, we are adding 1 to make it even. In this case, the message was already even, so we are adding 0 so that it should remain even, and now you would be transmitting this signal. So at the receiver end, if this signal is received, it would be passed because it has got even number of ones. In case if there is some error which exists, in case of error, what happens? We either a 1 is corrupted or a 0 would be corrupted. In this case, for example, the second bit is corrupted and this has become 0. So what would happen? We are getting the odd number of ones, and this message would be rejected by our receiver. Similarly, in this case, if we are having some error, for example, if this bit is an error and we are received with this bit, so we can see that there is some odd values which have been received, so there is some error or the message is corrupted. In case of odd parity, what we do, let's take on the same example, 1101, we add an extra bit. In this case, the parity bit is odd. In this case, it was even. Here what we are doing is, we are encoding every message bit in odd terms or odd number of ones. So here what we would be adding is 0 and our final bit would be, this is the message which would actually be transmitted. In the other case, we would be adding 1 and the final message would be 01101. Here what we are doing is, we are making the content, in our content we are making the total number of 1 as odd, and this is how it would be transmitted. If our receiver receives any even number of ones due to the occurrence of an error, it will reject that particular packet and it will request the data all over again. Now, how this is devised or this is designed. So, can we design the circuit which would look out for the parity bits or even parity in our case right now? Yes, we can. We have to first assign the parity bits. For 0000, it is, say, 0. For 0001, we can see there is only 1 or odd number of ones, we have to assign 1 here. In the second case, 0010, we have to assign 1 because there was odd number of ones. Here the number of ones are even, so we are assigning 0. Here the number of 1 is odd, we are assigning 1. The number of 1 is even, we are assigning 0. Number of ones is even, we are assigning 0, and so on. So, here what we have done, we have taken all the number of combinations from starting from 0000 up till 1111, or now we are assigning the values for every parities. In this case, in every case what happens, so what we are doing, we are taking all the possible combinations from 0000 up till 1111. Wherever the number of ones are odd, we have assigned a value 1 to make it even. Wherever the number of 1 was even, like in this case, we are assigning 0 so that this should remain even. Now we can assign this to a K-map, or we can design by using this in a K-map by getting all the minterms. The minterms here would be 1, 2, 4, 7, 8, 11, 13 and 14. So these minterms are put on this K-map for solving. 1, 2, 4, 7, 8, 11, 13 and 14. Now, there is no combination that can be made, so we have to take all of them as singlets. So for this singlet, we are having the value of A bar, B bar, C bar, D. For this particular singlet, we are having a value of A bar, B bar, C, D bar. For this singlet, again A bar, B, C bar, D bar. For this singlet, it is A bar, B, C, D. For this singlet, it is A, B, C bar, D. For this one, it's A, B, C, D bar. Then for this one, for the last one, by solving this using Boolean, we can combine them. Now, this equation can directly be put by using basic gates, but it's better to use some special gates, so we would be further solving it. So, on further solving it by using Boolean, what we are getting, A bar, B bar, where C bar, D and C, D bar can be extracted and A bar, B bar would be taken common. Similarly, in this case, we can take A bar, B as common. We are extracting C bar, D bar plus CD. Further, so just what we have done, we have taken few values common and we have extracted the other values. Here what we have got, C bar D plus CD bar, which is in the form of C XOR D. Here we have got C bar D bar plus CD, which is in the form of C XNOR D. Now this can further be processed. We can take these two as commons. And in these two, this whole term can be taken as common, so we are having now the equation is reduced to this. Now this can be written in the form of A XNOR B, whereas this one is C XOR D. Similarly, this term is A XOR B and this term is C XNOR D. What can be done is we can take X as A XOR B, and we can take Y as C XOR D. So this equation can also be written as X bar Y plus X Y bar, which is again in the form of A XOR B, or we can write it like X XOR Y. By substituting the terms again, what we are getting is A XOR B XOR C XOR D. Now we can realize the circuit by using just 3 XOR gates, which would be much more easier than getting the circuit through these basic gates. So this is the circuit which we finally got. Now what does this circuit do? It detects the input. Every combination can be given as an input. If the total number of ones is even in this case, what we are getting is 0 as an output. That means no correction is required. If the total number of ones in this case is odd, so what we would be getting is 1. That means a correction is required at the receiver end. This same circuit can also be provided at the transmitter end, where it detects all the incoming message bits and it adds up a digital value 1 in case if the message bit has odd number of ones, and it adds 0 if the message bit has got even number of ones. And this is how the circuit performs, and we detect the errors in a given message. Thank you so much.